Alright, now we have part C. So problem 21, in the diagram, each of the 4 circles has radius 8 and is tangent to 2 other circles. The centers of the circles are the vertices of a square. To the nearest integer, what is the area of the shaded region enclosed by the 4 circles? So here, to help us, we need to first draw some lines. So we will connect the centers like this. So now, since it's radius 8, each of these sides have length 16. So now to get the shaded region, we can do, so let's say shaded region, we can do the square subtracting the 4 semicircles. So now the square we know is 16 squared, which is 256. And then the 4 quarter circles, they form a full circle with radius 8. So this is 8 squared pi. Since if we think about these 4 quarter circles, we can rearrange them to form one whole circle. So this is 256 minus 64 pi. Using our calculator, this will be roughly 54.94. And so our answer will be 55, which is to the nearest integer. Next, we have problem 22. Out of the 100 people who are watching a movie, 47 bought popcorn, more than 40 bought a drink, X bought both popcorn and a drink, and 2X bought neither. If X is greater than 0, what is the largest possible value of X? So here we need to draw a Venn diagram. So let's draw like this. Here we have everyone who's watching a movie. We have popcorn, and we have drink here. So we know that X bought both, and then 47 bought popcorn, so 47 minus X bought only popcorn. We know that 2X bought neither. And so now we need to figure out how many people bought a drink. So since in total this is 100, let's call the number of people who bought a drink but not popcorn Y. Then we know that 47 plus Y plus 2X is equal to 100. So now we know that Y is equal to 53 minus 2X. So we can erase this and write 53 minus 2X. So now we can substitute this in for our inequality where more than 40 people bought a drink. So we know that the number of people who bought a drink was 53 minus X. Since we need to take into account this and this. And so this is more than 40. And so we have X is less than 13. And so the maximum would be 12. So the answer here is 12. So now we have problem 23. For some distinct positive integers p, q, and r, the integers 2r minus 21, 3r minus 1, r plus 12, and 3r minus 17 are equal to the integers p, 2p, q, and 2q, but not necessarily in that order. What is the sum of all possible values of r? So we could use casework on which is p or q, but we can simplify that a lot with one observation. If we look at 2r minus 21, no matter what integer r is, this will always be odd, because 2r will be even, and then when we subtract odd from even, it will be odd. So 2r minus 1 is odd. So this means that it cannot be 2p or 2q. So this means that this is not 2p or 2q. So now we can do casework on which of the other numbers is 2 times 2r minus 21. So here we have case 1, 2 times 2r minus 21 is equal to 3r minus 1. So as a solution, this gives us r equals 41. So now we just need to plug this in for the rest of the numbers. So we have p to p, q to q, b 53, 106, 61, and 122. And so this works. Next, for case 2, we have r plus 12 is double of 2r minus 21. So solving this, we get r equals 18. And if we substitute it back to the 4 numbers, we get 2r minus 21, 3r minus 1, r plus 12, and 3r minus 17 to be the numbers 15, 53, 30, and 37. So we see a clear p and 2p in the numbers 15 and 30, but the other two are not q and 2q. So this case has no solutions. Finally, we have case 3, which is that 3r minus 17 is double of 2r minus 21. So this is equal to 3r minus 17. If we solve this, we get r equals 25. Now, if we compute the other two numbers, we see that p, 2p, q, and 2q are 29, 58, 37, and 74. And so this works. So now this means that r equals 41 or 25. And so their sum is 66, which is the answer. Now we have problem 24. In the 6 by 6 by 6 cube shown, C and F are vertices, and A, B, D, E are midpoints of the respective edges. The intersection of AF and EC is G, and the intersection of BF and DC is H. A piece of the cube is removed by slicing it through the plane ABF, and then another piece is removed by slicing through the plane EGHD. This process is repeated on each of the 4 vertical edges of the cube. Let V be the volume of the remaining piece of the cube. What are the rightmost 2 digits of V? So here, the first thing to notice is that on these operations on the vertical edges, so let's draw in the other one, we notice that they don't overlap. So as we can see, one cut is here and the other cut is here. So now this tells us that we can treat each one as independent and then just multiply by 4 at the end. All right, great. So now we just need this. So this is a 6 by 6 by 6 cube, and we see that there's 2 main shapes. One shape is the ABFC shape, and if we mirror this, we also see that it's the EFDC shape. So this means that the cut area is 2 times the volume of ABF BCF, since the volume of CDFE is the same as ABCF, but then that overcounts this area by 1. So now we need to subtract the volume of CGFH. So first we need to compute the volume of ABCF. So this is a tetrahedron, and then since these are all right angles, we can use the formula, which is 1/6 of the product of lengths. So we know that A is a midpoint, so this is 3 and this is 3. So we have 3, which is AC, times 3, which is BC, times 6, which is FC. And then here we subtract the volume of CGFH. So let's redraw it a bit bigger here. So this is CGHF. So one thing to note, we can slice this across. So let's separate this into two shapes. Let's call this X. So now we have this entire volume is equal to 2 times the volume of CGXH. CGFH is equal to 2 times the volume of CGXH. And notice that this is the same, we can use the same formula for this, which is 1/6 of the product of the lengths from X, since these are also right angles. Now, since we know that E is a midpoint and G is here by similar triangles, this length is half, since the height is also half. So we know that CX equals 3 and GX equals 3/2. And so by symmetry, HX is also 3/2. So now that we've done this, we can do 2 times 1/6 times 3 times 3/2 times 3/2. And in total, this will get us 9/4. So now we can put this here, 9/4. So this is each individual cut area. And if we evaluate this, this is 18 minus 9/4. We don't have to simplify yet because we need to multiply this cut area by 4 for the 4 vertical edges. And so since we want our remaining volume, we need to subtract this cut area. So we have remaining volume is original, which is 6 cubed, minus 4 times cut area. So this is 216 minus 4 times 18, which is 72, minus 4 times negative 9/4. So this is plus 9. And so finally, we get that the remaining volume is 153. Since we want the rightmost 2 digits, we drop the 1 and we write 53. Alright, finally we have problem 25. The consecutive integers from 1 to 2k are written in order. Arthur erases k consecutive integers from this list. The remaining integers have a sum of 819. What is the sum of all possible values of k? So first we can use the formula for arithmetic sequences, and so we get the total sum is k times 2k plus 1. So Arthur erases k consecutive integers. we don't know which ones, but let's say let A be the smallest Arthur erases. So by setting a variable, we can simplify our calculation. So now, erased sum, we can use this formula again. This will be K times A plus A plus K minus 1 over 2. And this is equal to K times 2A plus K minus 1 over 2. So now if we subtract this, we get remaining sum, which is 819, is equal to K times 2K plus 1 minus 2A plus K minus 1 over 2. If we multiply by 2 on both sides, we can get rid of its denominator. So we get 1638 equals K times 3K plus 3 minus 2A. So now we know that K must be a divisor of 1638. So now we need to prime factorize. If we do that, we get 2 times 3 squared times 7 times 13. Now next thing we can notice is that there are some limits to A, so we don't have to blindly test every single pair. If A is the smallest number Arthur erases, then A has to be between 1 and K plus 1. Since if it's greater than K plus 1, then there aren't K consecutive integers after that to erase. So now we can do some bounding. 3K plus 3 minus 2A, we write, is greater than 3K plus 3 minus 2 times K plus 1, which is equal to K plus 1, which is greater than K. So now we know that this divisor, 3K plus 3 minus 2A, is greater than K. And since they multiply to 1638, we only have to test the divisors where K is the smallest one. So we can write all of those pairs out. So K comma 3K plus 3 minus 2A would be equal to 1 comma 1638, 2 comma 819, 3 comma 546, 6 comma 273, 7 comma 234, 9 comma 182, 13 comma 126, 14 comma 117, 18 comma 91, 21 comma 78, 26 comma 63, and finally 39 comma 42. So this is still a lot of pairs, so we can use the other condition. So by bounding this, we have 3K plus 3 minus 2A is at most 3K plus 3 minus 2 times 1, which is equal to 3K plus 1. So now if we plug in K to this equation from this, then we know that 3 times K plus 1 should be greater or equal to the other number. And so out of these pairs, the only ones that satisfy this are these, since 3 times 26 plus 1 is greater than 63, and 3 times 39 plus 1 is greater than 42. So now using this other bound, we only have 2 pairs left. So all that's left is to check these. And since they